So today we're gonna spend a little bit of time together today, um, building a natural language to SQL solution, or nowadays the cool kids call it NL2SQL instead of text to SQL, but it's all used. These terms are used interchangeably. And what we're going to do is follow along with this blog post, which I'll include in the video description, as well as a GitHub repo that I've actually forked and have been working from for maybe 3 or so weeks now. So I've got it in pretty good working order. I would suggest, if you want to fork the original repo and have all the fun and learn all the lessons that I did along the way, be my guest. But I would say a good place, probably a better place to start if you want to get up and running quickly, would be the repo that I will also share. But anyway, this is a really good post. It explains, like high level why we want to to consider a text to SQL solution. Also, let me grab the README that is part of the repo. So here we go. So it's a repo, published by AWS. So it is legit because it's great. We're using AWS services for this. And this combined with the actual blog lays out a good foundation. And the TLDR here is, what if we have a bunch of data and a very small team of people who actually know SQL? Like what if we're a product manager? What if we're on the ELT, the executive leadership team? What if, insert scenario A, B, or C here. You want to understand the data. You want our data, but doggone it, you got to submit a ticket every time, or, escalate something every time that you want a basic question answered. Well, fear no more, because this solution will allow us to implement a way for folks who don't have a comprehensive knowledge of SQL at their disposal. It'll allow them a way to empower themselves and query the databases, our databases, using natural language. Okay, so I will include the blog and the actual repo in the description. And so without further ado, let's get started. We're going to cue the Disney theme music here. Do you want to build a sequel, man? This is the story of Elsa and Anna, except not really. No, I'm just kidding. Those of you guys who know me know that I can't go too awful long without a really crappy joke, and that was my overly obvious attempt at making a stupid joke. Okay, so yeah, just a shout out to the blog post and the README again. Links to those here, as well as in the description, and kind of what we're going to follow just in terms of overall theme of today's video, as well as the code walk and jumping into the console. What we're going to do is follow this general format. Bring back the old slide deckosaurus. There we go. So our adventure today, it begins with setting up a data source. Technically, it begins with setting up your IAM role, or at least that's what I tell myself late at night when I'm freaking out, having panic attacks because I can't get the role that I've chosen to work with the project that I'm trying to build. Anyway, seriously though, choosing a correct role is to me foundational for any AWS based project. So that's why I've got it like technically you got to start here. So yeah, we'll save all of those deliciousness Funyun rings until we get to the console where we take care of that. But for the purposes of this proof of concept project, which is ultimately aimed at increasing internal productivity, data source, data source, data source. We're going to go with S3 as our data source for today. But as you can see over here to the right-hand part of the slide, we can hook this pipeline up to canonical databases as well. And so now that we have our storage taken care of, we got to give these buckets some data. So actually, let's pause right there. Let's jump over into the console because I don't want to get this. I don't want to like have too much theory and then circle back and then I'll go all the way through it and things just kind of like seem out of sync. So we're going to do this as synchronously as possible. I'm going to use the patient ping non-prod analytics sandbox account number 6888911 88534. I'm going to use that account. Excuse me. And go to S3. And so I've already, speaking of data, like getting data into storage that we can use for this project, I've already done that. And let's find that S3 bucket super duper quick. I'm not going to redo that just because it's like, it's so simple to put, load data in an S3 bucket. I don't think it's worth taking time out of your busy day to show you how to do that. I would assume that you guys probably know how to do that. So here's the name of the bucket that I created. It's for our raw input data because for this project in particular, we have two different types of data. And we have two different S3 buckets for those different types of data. The first, as mentioned, it's our raw data. And for this example, we're going to use IMDb data. What does that even stand for? I don't even know. IMDb. It stands for, I don't know. I am International Movie Database, I would assume. I'm taking a stab at it. I have no idea. We're going to assume that it stands for International Movie Database. Here we go. Data store text to SQL. The instructions in the README say to create a folder in the bucket called input, which I've done, and choose any file that you want to choose for this example. I just went, there's no rhyme or reason here, but I went with a file called basics. It's a comma separated file. I'll show you that real quick. Should be in the downloads folder. All right, yeah, so basics. Here we go. So we've got type of movie, primary title, original title, just in case the primary changed somewhere throughout the evolution in the filmmaking process. Is it an adult movie? I have no idea what that means. The brain can go off on many adventures when you're thinking about that. I'm not even gonna start that adventure. These are apparently some classics here. I think this is in ascending order, but we got movies way back in the day. Sometimes it looks like the end year is blank or not entered. Total runtime in minutes and genre. The unique identifier for all of the entries in this particular table is TCONST. I'm not going to pretend to know what that stands for. And since we're already in here, let's go ahead and I'll show you the other table that we're going to use, which let me see, you might have seen it. Ratings. It's a smaller table, and ratings, bring you up here, only has 3 columns. One is the unique identifier, the TCONST. 2, that's fine. Average rating and the number of votes, assuming that the number of votes were the total number of votes that went into the calculation of the average rating. So these are the 2 tables that I grabbed. Those are the 2 tables that we're going to use for this project when it comes to using natural language, letting AWS services, specifically Athena and Claude, Claude being the LLM in this particular example, generate SQL for us. And then we're going to test the accuracy of whatever is returned based on the questions that we ask. We're just going to write basic standard SQL to test the accuracy of the model. Okay, so I've shown you the 2 different tables. Keep those guys around. And I'll go ahead and get to this because there is, when we create a knowledge base, this factors into knowledge base creation, and we use a JSON L or JSON lines file to create metadata, to give our Claude model some metadata so that query construction can be a little bit more well informed. A lot of folks nowadays, if they don't have a JSON L type of file for their project, they'll use a graph database approach, basically create a metadata type of file or system to store metadata using a graph-based approach. And so you can see here we've taken a look at 2 different files so far. We're going to create this IMDb stage, and we've taken a look at the basics table, all of the columns. So we've got our primary key defined here, and it's also, since it's a column, we also have to define it further downstream. But this has all the columns that we've just seen, and then we have the ratings table, which has the primary key defined explicitly, as well as the columns that appeared in there. And so that will serve as our metadata. Again, with all of this with a nod towards making SQL generation as accurate as possible a little bit later. Okay, so let's back out of here. We've got our storage taken care of now. We've given our buckets some data, and now to create the metadata that I keep referencing, we're going to use our first AWS service that's not S3. We're going to use AWS Glue. So that's the next step. And let's back out to the presentation. So over here to the right, we've got step 1. And what we're going to do now is use the data to create our catalog, which would be the IMDb_STG_stage. And we're going to use AWS Glue. We're going to create a crawler to get metadata about our actual data, and as well as create a couple of tables in Athena under that catalog name. And we're not going to name anything different. We're going to keep the basic and the ratings named the same. So let's go ahead and jump back in over here and do that. All right, so we fire up another service. Let's go ahead and duplicate this guy and find AWS Glue. Okay, so over to the left, what we're gonna go looking for is the crawlers section. um, we can actually take a look. Here's the database that we've already created that has our basics and ratings. Actually, I'm not going to create a crawler. Let's just keep on going because it's not. It takes a little while to create a crawler, and honestly, it's not doing anything super crazy technical behind the scenes that warrants any sort of in-depth explanation. It's just, we specify our database name, we load, we point the crawler at our files, and then we create a metadata source as well as we load these two tables into Athena. So, yeah, we'll not worry about that. But I'll show you the crawler real quick. And if we were connected to a live data source, such as one of our databases, we could set the crawler up on a schedule. So to create a crawler, we would click on the orange button way over here to the right, give it a name. Let's see if I'm sure it'll let me cancel out. Have you already is your already data mapped to glue tables? We would select not yet. Add the data source, which would be our S3 source, and then keep on trucking from there. But since we've already done that, I've given it the IMDb crawler 2 because the first crawler I built wasn't very successful. I attached it to an incorrect role, and so it didn't work. Anyway, back to like if this were a live connection, we could schedule this instead of going in and like manually running the crawler anytime we wanted to run it. Because these are static tables though, there's really no reason to schedule it, and there's really no reason to go ahead and rerun the crawler right now. But yeah, big picture is that from this, we get our metadata, and we get our two tables zipped over to Athena, where we can verify our crawler functionality, make sure that the data has been extracted appropriately from the CSVs. And before we get any farther, why don't we do that? So again, we'll go duplicate and go to Athena. All right, our data source is here. As you can see, once you run the crawler and fire up Athena, you will be able to see your database. In our case, it is IMDb staging. And then we are also able to see our two tables. And here we can just take a look at any slice of the data that we want. It looks perfect, so nothing, no errors, no egregious errors or anything like that. Let's see. Oh, this is a question that we're going to use to test the overall app functionality when we get to that part. So anyway, let's keep on moving, and let's pull up our diagram here, check to see where we're at. Okay, so we've created our metadata. We know that the Athena is able to query it. And again, it did, whether it's an S3 or Athena or whatever, we can totally, point this at Starburst. We can point this at Redshift, doesn't matter. I'm just taking you through an example that's specific to this use case. And one of the reasons that, all databases have this kind of functionality baked into their logs and traces, it's that one of the big drivers for using Athena here, or any sort of logging, is that Athena, like all the other sources, are really good at pointing out when you have made syntax errors. And that is a really helpful piece of information when it comes to creating some sort of corrective mechanism for our overall model here, right? Because that was actually part of the the blog post. It was actually in the title. Build a robust text to SQL solution that can generate complex queries that is self-correcting. And the self-correcting part comes largely from what appears in the trace or the log of Athena when when we send off like a a Hail Mary type of query to begin with, knowing that we're trying to translate human language into SQL, and we're just doing so off the fly really quick. More than likely it's going to generate an error, but we get to use that information to feed to Claude to help self-correct our query. So really cool stuff. Okay, next up is although AWS is, just touch base on Glue really briefly again. Although Glue it can transform data sets, catalog data, as we've seen, as we're looking at right here, loading it to S, or not S3 but Athena, aggregate data, direct. Glue can even like direct uploads to S3. So there's so many things that Glue can do, and we're just looking. We're peering over the edge into the box on Christmas Day here, the box of Glue, and we're just checking out some really basic functionality. We've used it to create metadata, and we've used it to populate a catalog here in Athena. It's also really good at inferring schemas, discovering partitions, inferring data formats, and so on. And that's why it comes in now. So if we have data about our data, then we can fold in a RAG component into our, no pun intended. We can fold in a RAG, sorry, dad joke. We can fold in a RAG component. And that is where kind of the secret sauce occurs when we're trying to map some sort of RAG functionality to our SQL generation. Because as we all know, retrieval augmented generation, or RAG, is a way to let a large language model have a little bit more insight under, to take a peek under the hood at specific industry, specific to our industry data. And so with our Glue job to create metadata, and what comes next, which would be to split and chunk and embed that data, we can actually implement a RAG solution here. Fundamentally, the RAG solutions always involve some sort of mapping of the user queries embeddings to the stored data, their embeddings, and so that's exactly what we're trying to do here, to bring in a little bit more context specific flavor to our use case, so that our SQL queries, when we develop them, are even more targeted and more specific to our particular data domains. Okay. So, sorry, that was a lot of words. Just wanted to try to explain that as best I could. And now, once we have our metadata, we're on step 2, way up here at the top. Once we have our metadata all good to go, as mentioned, we're going to split it. In this case, it's done programmatically with lang chains. Where did we go? Here we go. Recursive character text splitter. Sorry about my dogs barking. They're very distracting in the background. Maybe you guys can't hear that, but it definitely is distracting me. I'll try my best here. So we use LangChain's recursive character text splitter to split split the data. Chunking is configured during the development of our knowledge base, which we'll get to here in just a second, as is the embedding step using the Titan text embeddings v2 model. Creating our vectors then is as easy as clicking the sync button, which I'll show you guys here in just a second from within that console. And once we do that, our embeddings are stored in the vector database. Amazon's Open Search service, for example, takes care of that. It also takes care of our similarity searches using FAISS. I think that's pronounced face. And that takes us through the first 4 steps. And so now, I said I would show you guys kind of like how all this, like steps 2 and 3 and 4, 5, basically the rest of the pipeline, how all of that works. It goes pretty fast, but do keep in mind that a lot of things are happening simultaneously. I'll give as much attention to every component as much as feasibly possible, but do bear with me in case I accidentally gloss over something. But anyway, enough words, Joe. Let's dig in to creating the very next step, which would be our knowledge base. All right. So we got our crawler, we got our query. Next up, let's go. Let's do what we've been doing, just duplicate that. That way we've got something Amazon specific here, and we can just grab a service. In this particular case, it's going to be Bedrock. That's how we create a knowledge base. All right, and then once we're here, we're going to actually go down to knowledge bases. And as you can see, we've already created one. I've created this one, NL2SQL knowledge base. Let's go ahead, because this is a little involved compared to some of the other previous steps, like the glue crawler was not that involved. Creating an S3 bucket, loading data to S3, not that involved. But I do think it's worth taking a moment here to show you guys how to create a knowledge base. It's worth the stitch in time. So I'm gonna leave everything. No, actually, let's go knowledge base name. Let's do, let's call it delete afterwards test during walkthrough. All right, anyway, there we go. IAM permissions, create and use a new user role. So what I'm going to do is go ahead and use one that I've already got. We could create, oh wait, no. This is a service role. This is a service role. So let's go ahead and create and use a new service role. I was thinking of policies for some of the other stuff. All right, so create and use a new service role. That's fine. We're going to use S3 as our data source. And what we're going to do this time around, instead of using like our raw data, which is what we did with the glue jobs, what we're going to do now is use our JSON lines file that we've also loaded to S3. Oh, I think I accidentally. No, we're good. We're good. And let's see, what did I call that one? Knowledge base text to SQL. And that's where we find our JSON L or JSON lines file. Okay, so that's why we're gonna point S3 at. We're gonna leave everything as is, click next. Create a new role name. So this will be, let's do Carhartt knowledge base temp delete after test. All right, that should be descriptive enough. Okay, click next. Data source name, knowledge base, quick start. Again, I'm just making sure that I'm including the word delete in there so that things don't get all gummed up. And at least I know to delete it. All right, so our data source location, that's going to be S3, and it's going to be associated with our account, the PP non-prod. Let's go point that. So that was, if I remember correctly, type in the word no for knowledge base. So yeah, choose that. Chunking and parsing configurations. I've left it as default for the POC. You could probably choose different chunking strategies. Yeah. Okay. So it looks like it's token based. You could probably get really fancy with it. I didn't bother. Just left it as default. I think it would be cool to experiment though for the next iteration. As mentioned, we are using the Titan Text Embeddings V2 model for our embedding step. So let's go ahead and select that guy. We're going to leave the vector dimensions as they are. What we can do here is we can go in ahead of time and we can go in ahead of time and create a collection in AWS's open search service, or we can let, since we're already at this step, we can let AWS do the lifting for us. So what, in a sense, what we're trying to do here is figure out what we're going to use as our vector database. Let's go ahead and do like the quick, create new vector store, which it opens up. It should go to open search. Click next. Okay. So here we're just getting nice. Okay, so making sure that all fields are as they should be. Account ID. I'm just making sure that we don't have to supply like a any sort of additional information. So I think we're good. We can create the knowledge base. This can soak up a few minutes. So while it's doing that, let's talk about next steps. Let's go ahead and figure out what we're doing next. So we've used the glue job to create metadata as well as a catalog of data that now lives within Athena that we can use Athena to query against S3. That's how to imagine, I think, a way to catalog our data. We have also implemented a RAG framework because what we're doing right now, we're creating a knowledge base with data that has been embedded, and the whole concept behind getting your data, your domain specific or your industry specific data embedded and living in a vector store is so that you don't have to rely completely on the LLM's training data. You can give it data of your own, and that was the whole point. Okay, so it looks like we got done back here in the background, and let's test it out. Let's see what we got here. Okay, so the knowledge base has been created. The vector database is looking good. And let's see if we can get any sort of response out of this. Let's go with Anthropic's Claude because this is what we use down here when we're doing the self-correction part of the user query. So let's just use that. All right, so we got Claude, one or more data sources have not been synced. So yeah, it looks like, so this part, even though we've created the knowledge base, we've pretty much applied the configuration settings to what we're gonna do. We now need to sync our knowledge base, which takes the data in S3, the JSON lines file. And when we sync it, when we press this button, like I'd mentioned way back at the beginning of the presentation, what we're doing now is taking this raw data and we're creating vector representation. We're creating embeddings that's going to go live in our vector store. So not only will we have metadata about our raw data living in the vector store, we'll have data about like metadata, like embeddings for our metadata in addition to embeddings for our actual data. So hopefully that makes sense. So we'll sync it. I don't recall this taking too many moments, so we'll let, okay, good. So yeah, I was right. I'm not a crazy person. You'd be like, well, that's up for debate. So one sec, grab a sip of coffee. Okay, and now let's see, tell me about your meta, not meat, metadata. Bummer. Oh well, that's not important for the purposes of this demonstration. Okay, so now we are actually done with the console side of things, but we are going to keep Athena handy here. And now we're going to go over to the goodness, to the code. And I've got the files from the GitHub repo kind of tiled out here from left to right. I'm not saying that these are fired sequentially like this in any sort of chat assistant or large language model application. It just doesn't work that way. We've got synchronous stuff going on. We've got sequential stuff going on. We've got asynchronous stuff going on. So it's, and that's kind of like by design, because, you know, to speed things up, it makes no sense to do things sequentially, because that would take forever. But if we were to try to imagine this thing in some sort of linear sequence, that's how I've got the files laid out across through here. So first and foremost is we got to get a way for our IDE to communicate with AWS services. That's what Boto client is all about. We create clients for each of the services that we have worked with so far. So for like Bedrock and Athena and S3, those are the three primary services. Apart from that glue job, then we, because we're, you know, asking, we're not posting any sort of user query within the console. We're doing it here out at the IDE, and so we have to have a program that allows for us to chunk and split and vectorize or embed the user's query side of things, and that's where this comes in. Also, if we want to just take care of all the configuration things within the console like we just did, we don't have to go back to the console ever again. We can totally do things. In fact, that's the only way I've been doing it is to do things from your IDE. Okay, so we've got the vector embeddings file. Let's see. So I'm trying to think if there's anything here to really dig down on, and nothing super like, yeah, we nothing really super interesting there. It's just a way to embed it's where we specify our embedding models, provide the configurations for doing so, provide functions for doing so, just boilerplate stuff. Here is where we can tinker around with choosing a different set of LLMs to mess around with, or different configurations. Like right now we're running a temperature of 0, a top K of 20, top P of 1, and then let's see. Yeah, we got our Titan text embeddings and Anthropic Claude specified here. That's what we could tinker around and test if we wanted to test that. I think it's maybe just a little bit beyond the scope of showing this high-level overview to explain what temperature, top K, and top P are, but they're just a way to apply constraints to your model and its predictions. I think that's keeping it as simple as possible, because ultimately that's what these parameters are all about. So I'm not going to get into the weeds. We'll just leave it at that. This particular file took the longest for me to figure out. And it's because the vector database sits right in the middle of all of this. It's downstream from storage and the glue crawler job, and it sits upstream from all of our querying. And it wasn't the functionality as it relates to the vector store and how that maps to anything else that we're doing. But what took me the longest to figure out is permissioning. So those IAM roles, that's what took me the longest to get this file working. So let me explain a few things so that you guys, if you were to jump in and try to fork this repo. And by the way, like I would suggest reaching, if you want to do this same thing, please reach out to me. And I've got this repo forked and I've been working from it to try to streamline it for this particular use case. And the next step would be, our actual data use case. It's a whole lot cleaner. It's a whole lot easier, I think, to use than the raw format that AWS provides, just because it's so generic in general. So reach out to me, and I can give you all of this information, the link to the repo, and after I explain what's going on here, then you should have no growing pains like I unfortunately had to endure. So OpenSearch domain endpoint, where we want to grab that is we go into our console, and remember when we created our knowledge base and we kind of hand wavy let AWS services take care of building the vector database for us. That's where this comes in. So we go, we open up OpenSearch, go to our collections, and the one that I created off the fly, not just now, but back when I was developing this, I called it text to SQL OpenSearch. And once we that's when we were back here doing our knowledge base, and if we were to give it a name instead of this kind of blah stuff right here, oh no wait, this blah stuff, then that's where I named it something a little bit more I'll remember this, because this project is about text to SQL. Pay super close attention here, because this is in addition to IAM stuff, this did cause a little bit of growing pains. And so you'll notice here, vector index name, vector field name. You're going to have to go into OpenSearch and create these, because you do rely upon these. Index name, you also need your endpoint, but you need them again down here, right here, in the main function. So you'll need your index name, you'll need your vector field name, you'll need your domain name, which are the same as above, and you'll need this field name, which is associated with our metadata. Have to have those. Can't emphasize how important that is. So let me show you again where to grab those. So let's say you've just created your knowledge base and you've got this wonderful green banner across the top and you're just like, yeah, I'm super close to being Dunyan Rings, Funyan Rings. And you're pretty daggone close, but you do need to open up the Open Search service, go to collections, find the collection that you've just created, grab your endpoint, which is right here. So it's EOHCOO I67. Let's just make sure that matches up. EOHCOI. So yeah, that's exactly what we need. From this page though, you'll notice where's my index name? Where's my index name? I don't see it. Well, that's because you have to go over here to indexes and create one. So this will be blank once you find your collection. You'll open it up and you'll have the opportunity to create a vector index. And this is just a way to map what has been embedded back out to your original raw data. If you don't do this, there's no way that this RAG framework portion is gonna ever work. So it's definitely worth paying attention really closely right here. I know I'm belaboring the point, but this is because I struggled so much with it. I got in a big hurry and it took me some minutes to figure out what I was doing wrong. So key pieces of information, your endpoint right here, click on index, create your index with this either one of these two buttons, doesn't matter. Once you create your index, then you will have some data here. Click on that, and then that is you'll have an opportunity to go in and give these fields their names. And so since we've created our index, we give it a name. I've called it text to SQL index. And your vector field, it should have like a plus button or something like that. And I've called mine embeddings vector. You call it anything you want to. I just figured it made the most sense since we are talking about embeddings and our vector store. The engine I've mentioned to use for similarity searches is the FAISS, FAISS. Make sure our dimensions here match to what we selected when we created our knowledge base, which is 1024 for the Titans text embeddings. This is super important because, again, your model will not work unless these dimensions match. Okay, go back to OpenSearch. The type of proximity or similarity function that we're using is Euclidean. We could use like dot product. We could use, I think, cosine similarity. Maybe there might be one more. I'm not super sure. But those are, I think, when you use like the little wizard in the knowledge base, like, yeah, go ahead, AWS services, go ahead and create the Open Search vector database for me. I'm pretty sure that these dimensions right here, like maybe even the 1024 embedding size, I'm pretty sure all of those are pre-populated for you. Again, probably beyond the scope of this to go into like the theory for like what all these actually mean. So I'm going to resist the temptation to do that. And now let's go back out to the code. So now you can see like where these are pretty important. So we put our index name in here. This is something I was talking to Tyler about, just how easy it is to open up your account in one availability zone. And then somehow, some way, or region, like end up in US West 1. And so like pay attention to these things if you're a new console user. I guess I would consider myself a pretty new console user. So it's worth really kind of pay attention to. Don't just like click through as fast as you can just to like get done. So yeah, so everything maps here. This is our endpoint, our index name. This is AOSS. I'm not sure what that stands for. This is an ignorant moment for me. I'll have to look up what AOSS means in terms of service. Everything else you leave alone. You don't have to change port or anything like that. And then we keep on scrolling. All of you leave those alone. Amazon Bedrock Test Chunk, leave those alone. And then you input your, this is the same thing as your vector index, same thing as above. Just copy and paste the same thing. Here's the embeddings vector that I mentioned for your vector field. This is the same thing as above, your domain. And field name, we leave as ID. I made the mistake the first time going into this and creating, let's see, serverless collections. You have the opportunity to do so. Like once you click on index, like create an index and then go in here and create your vector field, you have an opportunity to create metadata. And it was causing me trouble, like issue after issue after issue after issue, because I was thinking, well, I've got to go in here and create a metadata field called ID, but it was loading it as a string, but it needs to be recognized by the model as a dictionary. So the easiest thing that I found out to do is to just don't even bother. Leave this as it is, and the model, and I don't know how, this is a dumb Joe moment, the model figures it out. So you just leave this field name. It refers to that metadata where we could create a field called ID and give it some sort of value, or just create the value itself. It'll still cost, maybe it won't cause problems for you. It did for me. But I left this as is, didn't create any sort of field here for metadata, and it finally worked. Okay. And that's it for that. The only thing that I want to mention with Athena execution.py is this cool syntax checker. Like right now, and this is like getting more targeted to like, oh, I forgot what Joe is even talking about. He's talking about this service and that service and blah and vector and this and like, what are we doing this for again? We're doing this so we can transform natural language into a query that can be leveraged against our data and then return an accurate natural language response so that we don't have to know SQL in order to talk to our databases. That's the point. That's the Mama Jamma, the Tropicana Twister flavor that Mother Nature never intended but should have. And part of that awesome flavor stuff, like Skittles taste rainbow, that sounded creepy as crap, is the syntax checker function. And I mentioned briefly at the beginning of this is that, all databases, relational databases, Athena here, where I'm using Athena kind of colloquially, lumping it into that RDS kind of like category, just because of the logging. What is cool about syntax checker is the ability for us to use logs and get the error messages from the logs to in combination with the large language model Claude in this case, to create a self-correcting mechanism which we iterate over. Here it's like 4 times. I'm trying to remember where the config is for that, but it's something that we can adjust. Is we give our query 4 different passes to get it right. And shoot, I'll have to find that. But that's the magic sauce for the Athena execution. And then the what I want to call like the main file is this guy. This is the file that we actually run. and the only file that we need to run. Everything else is configuration, configuration, configuration. And this, if you were to fork the original GitHub repo, you'll notice that request query bedrock.py isn't in there. And that's because it exists as a Jupyter notebook. But I like Python files better than Jupyter notebooks. Like, ask me a year from now, and that may not be true. But I took everything that was in the Jupyter notebook and created a Python file from that. I just like running Python programs better than cells in a Jupyter notebook. You're more than welcome to go the Jupyter notebook way. But I'm just telling you this because it's basically the same thing. So yeah, this is what we run. And so here we use that same kind of information. We need that information again from our OpenSearch service. So your domain, you'll see that AOSS right there. I need to figure out what that is. Your index name, the region, and your vector name. Field name, leave that as is. Okay, and so what we're doing here is just, oh, here we go. Here's all the different attempts. Here's where we specify the number of attempts. And I'm pretty sure it sums to 4, if I'm not mistaken. But anyway, the most important, I've learned, apart from getting this information right up here, the most important part of this particular file is the following, the user input function. And it's called details. You can, those of you guys that are building and have built stuff, you can think of this as your system prompt or your system message. This creates, for one of a better way of saying this, and Chelsea, you're going to kill me. This creates guardrails, not the kind of guardrails offered by AWS, but this creates constraints. There we go. It creates constraints that your model needs. These large language models are great, but they can, even with a temperature of 0, you have to give these pretty clear instructions. And Jacob presented on this a little earlier. This is not what you would consider like prompt engineering in a purist sense, but it reminds me of prompt engineering in a way because you have to be very explicit in your instructions. And so I think the most important piece of this is this. And I only through hard knocks have learned that, oh, this is the format that it needs to be in. And this is what needs to be there, because it was pulling from data sources I had never heard of. But it was, if I had opened up Athena to include like more databases, like all of these guys, it was pulling from there, like trying to create queries based on like what my user input, like, hey, what's the blah, 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 whatever I typed. It was looking through all of these. Not just IMDb stage. So that was a very important little lesson learned. And so I learned, we have to be really explicit here in these constraints. So data source, AWS data catalog, that comes straight from here. Database, you'll see, is here. We're telling, do not go looking for any tables other than these 2 tables. And make sure that you only pay attention to the columns that are in those 2 tables. Don't go making up columns. And we're giving it the model the unique identifier, which is, as we saw way back at the beginning of this presentation, the TCONST. And so here's the instructions. Like, think of these parameters as the only available resources with which you have to answer the question. During a join, if 2 column names are the same, please use the aliases so I know which one's which. basics T-con C-O-N-S-T versus ratings C-O-N-S-T. Like, I need to know where you got this thing in the select statement. It's also important, application, to not alter the column format. For example, if a column is a string, then leave the thing a string. If you're writing CTEs, include all the required columns, just common sense stuff that we as humans take for granted. You have to be pretty explicit. And if you're concatenating a non-string column, make sure to cast the column to a string first. If you encounter any instances where we must compare date columns to strings, go ahead and cast the string input as a date and format as such. And remember, use only the data sources, databases, tables, as mentioned above, and always include the database name with the table in the query. All right, so we are super close to being able, or not able, but we're super close to being ready to ask some questions. I've developed 3 in increasing level of difficulty, but I mean, like, somewhat difficult. You can only expect so much out of IMDb. I'm kidding. But before we do, let's review what we've learned real quick, and then tack on the remaining pieces, and then we'll do the really cool to the beans, no faking stuff. All right, so we've covered the first 4 steps. Let's zoom through the remaining steps. So the query plus context. The context simply refers to the use of natural language in the query written by the user. Here, that's going to be me in just a few minutes. Quite literally, any details provided by the human user will suffice as context for an LLM to learn and infer semantics for query development. For example, we're going to ask about clowns here in a few minutes, not because I like clowns or think I'm some sort of edgy goth kid, but because the word caught my eye when I was doing this research, and it seemed kind of rare. Like, a word that if I filter on it, shouldn't return a bunch of rows. So the relevant context would be the original title filter, like title is, air quotes here, is like clown, because you can't use the contains predicate or operator. I can't remember which one's which. Predicate or operator in Athena. All right, so 6. SQL generation, the first stab. Man, I am full of like weird Halloween references all of a sudden, because every time I think of clown now, I'm thinking like Pennywise. So anyway, based on the user's query and content, a first attempt, step 6 here, of generating a SQL query is made. So if you're thinking, Joe, is this where we finally get to use an LLM like Llama or Claude or GPT? The answer is a big old resounding yes, my friends. This step here is kind of like a Hail Mary pass, and it is completely intentional. And that's because a first pass query is often imperfect due to the complexity of converting human language to highly polished executable SQL after one take. Y'all get my joke there? Take 1. We're talking about a movie database, right? And action. God. Step 7. SQL failure and error feedback. The loop, the cool loop. Even if you're trying hard, errors can and often do occur, sometimes with more frequency than we like to admit, especially with complex queries because of like syntactic issues. Real good example of this is like the stuff you get when switching from like PostgreSQL to Trino SQL to Redshift SQL, and remembering like the fine little nuances between each of those language for like wanting to do the same thing. There's 3 different ways. And so the error log or the trace serves as a really cool feedback mechanism about why and where the query failed, essentially providing us with a signal for what needs a fixing. Step 8. Claude to the rescue. So Claude or another LLM, your favorite, the one you want to like, take to the ice cream shop because it's your best bud. Um, Claude or your best bud LLM uses this error feedback to generate a revised SQL query. And we all know this by now. The LLM learns from the error details and reattempts the query generation process by correcting the specific issues that led to the failure. I use ChatGPT and speaking of Claude for this regularly. Grab the error that popped up in my trace and gives me something to try in terms of debugging, just like that. We're basically doing the same thing here, just in a more systematic and rigorous way. All right, so steps 9 and 10. So after the revision, the corrected SQL query is buttoned up and executed in Athena in this use case, or you want to picture it with some other backend database system, go right ahead. Hopefully we'll be doing that pretty soon. Anyway, wink, wink. With our encounter data. But anyway, this process continues until a valid SQL query is obtained, leveraging that error feedback iteratively. I cannot say that word. You know what I mean? That word that starts with the I that's hard for Joe to pronounce. Okay, so right on. So in the slide deck here, I've got kind of sort of what we have gone through in a roundabout-ish way during our time together. So again, the phases are more of a cognitive mapping as opposed to the mapping that you see here. I've just broken it out into 5 different phases, from setup to storage to the glue piece to the vector database and similarity search pieces to finally the development of a knowledge base. And so now with our understanding, we are ready to ask some questions. And those questions, I said I developed 3 in increasing levels of complexity or difficulty, are as follows. The first thing, and I'm just pretending like I'm a big shot movie producer in Hollywood, or just somebody in Hollywood, that's interested in learning some stuff, but I don't know SQL. So I'm like, how many records are in our database from the year 1892? If I don't know SQL, I wouldn't even know where to start. So because I do know a little bit of SQL, at least, we can take a stab at what this might look like. So let's oops, what's going on here? Maybe need to refresh it. I've been talking a while. So let's develop a query to this question together. And I hear a helicopter outside, which means my dogs are going to start barking, which means it's going to be really hard to concentrate. I'll try to push through. So what we want to do is 1892, right? So 1892, this would be the start year. Where's our start year? I'm not gonna, anyway, maybe I just need to reference basics, where start, gonna give me, nope, start year and this is a string, so we're just gonna do it like this. 1892, 400 years after Columbus has sailed the ocean blue or whatever. Okay, so select star from basics, where start year in 1892. All right, we've got 3 rows. So I can look at this as a human and be like, okay, so there's 3. But I'm more interested in what Claude does in developing, not only getting the answer right. That would be cool if Claude gets the answer right. But what would be even cooler is if Claude nails the correct SQL. So that's why we're looking for 2 pieces of information here. The first is, did Claude let's just comment that out. That way I don't have to like retype it. Did Claude get the answer right? And also, did Claude develop correct SQL? Equals Shazam. And all right, make sure everything is good to go here. Exit out of this. For some reason, when I like run the debugger, which I'm thank you, Tyler. Shout out to Tyler. I need to do often restart just because sometimes the debugger, even though like you think you've shut it down, it low key is like a pesky. Like growing up, you had that pesky neighborhood kid that like didn't understand. Hey, it's time to go home. Our time hanging out together has come to an end for the day, my friend. You just like, anyway. Here we go. All right, so let me fire this off. Actually, I'm just gonna like run debugger because again, it's way more fun than just hitting run because you get to see a whole lot more details. So don't pay any attention to this red stuff right here. Need to get a different color scheme. All right, so I think I've mentioned this previously. We're giving Claude 4 attempts to get it right, or that is to do the Hail Mary, receive feedback from the error log, do another pass, but with not a Hail Mary this time, a little bit more polished query, and essentially iterate over this green box step a total of 4 times before saying, all right, done. Hope that you're happy, human. So let's see what we got here. Just to refresh your memory, in case you're like, what are we looking for again? We are 2 things. We're looking for an answer of 3 because we've seen that movies written or excuse me, that were produced in the year 1892, there were 3 rows, so we should get a number back for 3 if Claude did this correctly, because what I'm expecting in terms of correct SQL is a select count star from basics where start year in 1892, so something along those lines. All right, should be wrapping up any moment here. Wish I had some cool music. Maybe actually I do. Let me see if I can find something. As soon as I push play, though, it's probably gonna be like, Oh, what do we got here? So select star. Checking for file. How many records are in our database? Weird. Let's try again. That's unexpected. So let's. Very strange. Maybe the elevator music will help this time around. But I've done this previously to try and save time. And actually, I mean, why don't we do that? Because I can show you that this it does it correctly, and it that way we don't have to like just sit here and like me look up dumb music while we're waiting. So let's go ahead and so we've seen how we would answer it with Athena, right? We've seen that we get back 3 rows. And what I've done is for each of these answers, prior to the presentation earlier today, is just go ahead and drop in what Claude ended up going with in terms of a final answer, as well as the SQL. So, the final SQL that Claude had for the first question was select count star from IMDb stage basics, where start year equals 1892, which is what I would expect if I were given a human like a pop quiz over SQL. Which is more, I think that's more important than the correct answer. I don't know. I don't know which one's equal, like should be weighted with greater significance. But anyway, batting 2 for 2 here because Claude got the answer right. We got the integer back of 3, and the SQL was correct. So next is the second question was, and this is a human, like what was the total number of votes for all movies with the word clown in the title? And so let's figure out the SQL for that. So we've got, this is what I would do if I were researching this. All right, there we go. Select a dot star from IMDb stage dot basics. Whoa, missed the letter there, and now we're in the wrong spot. STG. What's this? Yeah, for some reason this is not liking me right now. We'll try a different. We'll fire off the the second question while we're actually answering it here with Athena. All right, so heck with it. We'll run this one. We'll see what we get. Instead of debugging. Okay, let's answer the question. So select as a, and then we gotta grab. So we're looking for total number of votes and clown in the title. So we need number of votes for b.num. Where's our num votes? Inner join IMDb stage. Bloop. Ratings as B on A dot T const equals B dot T const. All right, and here comes our where clause. Where I think it was primary title. What happens if I click on it? Holy crap, that's awesome. It just populates. That was neat. Didn't know that. We're primary title. We can't do contains, so it's like clown. Oops. And what was the number? What was the rest of the question? Oh, just the total number of votes for all movies with the word clown in the title. Okay, so we just need these pieces of information. Oops. Run this. One row, where's our total number of votes? 282. So, from earlier, the good news is Claude did get it right. We got 282, which is perfect. And check out the SQL. Select sum from because if there's more than one row, we would definitely want to use the sum function. So sum ratings dot number of votes is total votes. Inner join, yeah, cool. All right, so batting 4 for 4, I guess. So let's go to the last and final question, which is as a human, I need all the unique IDs from the animation genre with an average rating of 5 or higher and at least 1,000 votes. All right. Oh, cool. Well, I don't know what was up with that first time, but so the second question, one with the clown, we're good. So replicated what I just showed you here live. So the curse of the live demo. As soon as I say that, like I'm gonna fire off this last one, and it'll probably return like you have 18 minutes to live. Something completely just inappropriate. But anyway, all right. So let's do the last query here. Fire it off, and then we'll go develop it together. I love hanging out with you. It's fun. We'll developing queries together. That's how you make friendships. Do. Okay. Making sure we don't have any little red marks. So I think we're good. The reason it's giving me the underline is because it extends beyond this this vertical line. We're gonna ignore that. We're gonna run the program. Okay, and then we're gonna go write the query. We're gonna repurpose this just to save a wee bit of time. All right, so what we need now is number of votes as well as average. Ooh, wait. I'm gonna, here we go. Double click it. There we go. How cool is that? So we got everything from the basics table and 2 columns from the ratings table. And we want primary title. No, wait, genre. Genre. For some reason, it's plural, where genres like animation. And this is an and instead of an or, right? Because it's animation and these other 2 constraints. So I believe it was average rating of 5 or higher and at least 1,000 votes. Average rating, and average rating. Oh, come on now. Ooh, wait. Try this again. I can't get used to the awesomeness. Average rating of greater than or equal to 5, and we're just layering these things on here like icing on a cake. And number of votes. I'm just sorry. It's the little things. Greater than or equal to 1,000. Let me just make sure everything lines up. I need all the unique IDs from the animation genre with an average rating of 5 or higher and at least 1,000 votes. So this should give me what I need. Okay, we got 5 rows, which if I wanted to be more specific and make a more polished query, then I would just get the unique ID here and be done with it. But yeah, we got 5 rows. Let's see. Claude's still thinking about it here. But that's what we should expect. We should expect Claude to churn out these 5 IDs. Let's see. Make sure I haven't missed anything. No, I think that's it. Let's see. There was something I wanted to follow up on. It was the AWS thing. So like let's do that. Let's while Claude is working its magic there. Let's go to here. Copy this because I wanted to know what AOSS meant. Boom. Already looked it up, and it refers to Amazon Open Search Serverless. So yay! Knowing is half the battle, as G.I. Joe says. And cool, we get our 5 IDs back that fits the constraints of the query. So let's check out the query. Select the unique ID. That's perfect because like if I wanted to take this one step further, I would just polish it and just select that column. So that's awesome. And the rest of the query is exactly like we've written in Athena up here. So yeah, we're good. Okay, well that ought to do it. I appreciate you guys hanging in there. Thanks for the attention. Like I said, if you want to follow along or if you have any questions after following along and something didn't work out, ping me and we'll get it ironed out for you.